on the assignments which you have done last time. I asked you to do a steady experiment of an DAC, which was an R2R DAC. Then I asked you guys to make amplifier and a T flip-flop. I know there were 4 experiments for the weekend, but I think ample amount of time to cover it. So anyone has a doubt or face difficulty in making any one of them, or something is there which you want to discuss, let me know. Just put on the door. Okay. There is quite a silence from the students. Yes, we can do a DAC once again. I will definitely. Hi, Kaushik. Yes, we will. I will open up the DAC. Then I believe I open it once again. Something. Okay, everyone is there on the chat and is in the front of the desk, so that I can start my chapter today. Okay. And okay. So during this training course, I intended to cover these experiments for for doing the purpose. I mean, so we have covered, I think, all of it. If something is remaining, let me know if I've missed it or skipped it. I believe I've gone beyond the list, but that's okay. I hope you guys don't mind it out of it. And I'm sure it will be to your benefit only. Okay. So there are a couple of things which have been missing, and as we have been running on a very good time scale, so to take a benefit of it, I will cover things which were not listed in this, and I will try to go and push the syllabus a little bit further. Okay, so today I intend to so today I intend to cover this DAC, and if required, we will do a case study of ADC if required. It's a very big experiment, quite a big one. Okay, and then I intend to cover IOs today. Okay, so these 3-4 experiments, and also the amplifier common drain, because that day we did common source. So today I will common drain, but that will be very quick because you guys have done common source, so you have understand the basics, and now you guys are very familiar with the layout, making everything. So we'll go faster now. How about starting the session now? Okay. Now let me see all of you are here or not. Let me check. And Abhishek, present, absent, Akshata, Amruta, Asya, Muskan, Charumati, Kalpana, Harshvardhan, Harshita, Pavitra, Kaushik, Krishnamurthy, Ankita, Meghna, Ahmed, Nandini, Prajwal, Raju, Redmi, CMO, Sai Nag, and Shaktidhara. Bapre, what's the name, yeah? Good. Shri Raksha, Shreya, Shruti, Suma, Swati, Tanmay, Ram, Varsha, Venkat. You guys there or not? I'm just. Uh, okay, great. Good to see all of you. So shall we start? Okay. So I have posted the list of experiments, and I believe we have covered most of them. So let me know if something is there or missing, because I believe we have only a couple of sessions left. Okay, so and Asani, it's not like this that I won't be foreseen forever. And anywhere later you feel any have doubts or questions, you can always message me or email me, and definitely I will reply on my comfort. But I will do reply. Okay. Okay. So during the weekend, I asked you guys to make and flip flop and practice the amplifier again, and also so that gave you, and I think, an edge on using the Verilog compilation option and simulate it to understand how the flip flop works in the layout, etc. Okay. Now today maybe we can start with an DAC, which was R2R. Okay. So have you guys have gone through the DAC concept, the theory of it? No? Okay. Okay, 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 okay. Just open the DAC and then I show you the screen. Okay. Mm. Sir, can you allow me to share my screen? Can you make me those, please? Hello.
Please just hold on.
Yeah.
Yeah.
Okay. I'm trying to find. Okay, I just trying to find the example. It was not found in the first shot. Let me find it again. Okay, guys, I believe you are able to see the screen. This is an schematic of an R2R. I believe you must have seen it. So this is a simple R2R ladder network. Okay. So this guy, it's a simple logic. Okay, where you have a reference voltage. Okay, and connected through a series network of resistors. Okay, so every resistor will give an corresponding voltage, okay, on the node, okay, of the value by the and resistor voltage divider resistor network, which allows, okay. So for example, in the first combination, it will give you half of the value. The second combination will give 1/4 of the voltage, third 1/8, and then 1/16. So that's why it is like, and every bit corresponds to the double of it. That's how our bit logic is also there. So LSB on the right hand side and MSB on the left hand side. Okay, so every bit will add that corresponding voltage to the same line. As you can see, that same line is being connected to the output amplifier. Okay, this is just a linear follower. You can put an amplifier also to it. Okay, so same example is available in microwind layout mass file. I believe you must have opened it, the same file which I gave you the link that day. Hmm. And let me share the screen. Okay, so, and I believe everyone is following what I'm showing, and there is no uh, absence of the kids in front of it. Okay, so this is it. So this is how this same R2R ladder network is being made up. The only difference is that on the bottom side, you have an NMOS driver, which will pull down the voltage if that bit is not being used. Okay. So that's it. So this every NMOS turns on and off, okay, the ladder network. But remember, the NMOS is a weak, driver of logic 1. Hence, he will be not able to pull down to the lowest of the minimum value, but still he gives a very good network. Okay, so I believe you must have just opened it and simulated this design file. So if you just simulate this value in default, so as and a squarish waveform has been applied, so you see a ramp signal. I believe you must have seen this one. So for a 0, 0, 0, you get the maximum value because all NMOS are off. All NMOS are off. So if all NMOS are off, so obviously the voltage is being pulled up to the max value of it. Okay, because all these values are added 116, 18, 14, 12, they are all summed up. Okay, so you get the maximum value at the output. But as you keep on turning on the bit by bit, like B0, so only one NMOS is on. So when one NMOS is on, a voltage slightly comes down because that NMOS has been turned on, and 1/16th value of that transistor, that node is being deducted from the output voltage. And when you become 1, 0, so that is 1/8 of the value, that value is deducted. And when you turn on the value 3, that is B1 and B0, both are on. So they will reduce 1/16 and 1/8 both from the output. So you can see the value comes down a little bit. Okay, and henceforth. So as you keep on turning on the NMOS combinations, okay, so the values keep on coming down. Now, when you see at this thing, okay, when all NMOS are on, so this is the least value he comes down to, which is around 0.589 or close to 0.6 value, he comes down because as you remember, the NMOS is not an producer of, like he cannot pull down the values to the lowest. At the minimum, he can bring it down to 0.4 or something, okay? So the voltage swing of this DAC is not maybe from 1 to 0, definitely, but it's from 1 to 0.6. So 1 to 0.6, that range you have to amplify or maybe use it further in your designs, okay? If you want to bring it down a little bit, so obviously you have to increase the current of the NMOS, okay?
Oh.
Yeah, you have to increase the size of the NMOS transistor, and that will allow you to pull down the values a
Yeah,
little
correct.
bit more.
Just
And
we started a class now.
okay.
Okay, again at 6 o'clock is okay.
So I just take another example of this. Okay, so here this is also in same design. Okay, and let me open this in another technology, Cmos 012, because most of the design these are made up in 120
Hello.
nanometer technology file.
No.
Yeah. So in this case,
seek the permission.
we have a DAC output that goes to a push-pull amplifier. Okay.
Okay.
So this is a push-pull amplifier
Sure.
which will give you an almost
Okay.
complete range of the supply.
Oh, okay. ನೋಡಿ ಮ್ಯಾಮ್ ಇವತ್ತು ಓಕೆ ಯಾ ಥ್ಯಾಂಕ್ ಯು.
So here you can see that this is the amplifier output. So here our main R2R ladder network output is able to go till around 0.2, and we are able to
Oh,
also go to 0.2,
yeah,
but the smoothness is much more better. Okay.
ಹಾ ಮ್ಯಾಮ್.
We have covered this. Yes.
ಇಲ್ಲ ಮ್ಯಾಮ್,
Yeah.
ಅದು ಆಕ್ಚುಲಿ ಅದು ನೀವು ಸ್ಪ್ರೆಡ್ ಮಾಡುವಾಗ ಏನ್ ಮಾಡಿ, VLSI ಇಂಡಸ್ಟ್ರಿನೇ ಬೇರೆ, ಎಂಬೆಡೆಡ್ ಇಂಡಸ್ಟ್ರಿ ಬೇರೆ. ಹಾ ಓಕೆ. ಆಕ್ಚುಲಿ ಏನಾಗುತ್ತೆ ಗೊತ್ತಾ ಮೇಡಮ್, ಮಾಡುವಾಗ ನಾವು VLSI ಸಪ್ರೇಟ್ ಎಂಬೆಡೆಡ್ ಸಪ್ರೇಟ್ ಮಾಡೋದ್ರಿಂದ ಅದಕ್ಕೆ ವ್ಯಾಲ್ಯೂ ಬರೋದು. ನಾವೆಲ್ಲ ಸೇರಿಸ್ಬಿಟ್ರೆ ಏನಾಗುತ್ತೆ, ಹುಡುಗರಿಗೆ ಸುಮ್ಮನೆ ಕನ್ಫ್ಯೂಷನ್ಸ್ ಆಗುತ್ತೆ.
Sir, there is an interference of voice.
15 ದಿನಕ್ಕೆ ಒಂದ್ಸರಿ ಆತರ ಮಾಡ್ತಾರಲ್ಲ ಮೇಡಮ್, ಏನ್ ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ.
For 2 minutes.
ಈಗಿರೋ ಹುಡುಗರು ಮನೇಲಿ ಇರ್ತಾರೆ, ಇನ್ನ ಒಂದ್ 2 ತಿಂಗಳು 3 ತಿಂಗಳು. ವಿಲ್ ಡೂ ಇಟ್ ಮೇಡಮ್, ವಿಲ್ ಡೂ ಪ್ರಾಪರ್ಲಿ. ಯಾ ಥ್ಯಾಂಕ್ ಯು.
Okay, now I think I can mute the host also, no problem. Okay. So this is an DAC with an amplifier at output, so that you can smoothen out the output and go a little bit more on the range. So instead of 0.4, I can restyle 0.2. Okay. Someone wants to say something, because I see some videos popping up. Road track. Okay, no problem. Might be a mistake. Okay. So this looks good, and to the scale. Okay, now let's make something nice out of it. So if you think of making, I remove this delay and bus value so that I can see the slope coming better. Okay, so let's say if you wish to make use of this DAC to generate a sine wave, how you do that? That's a complicated job. That's not that easy. Okay, that's one question. Okay, and the power consumption, etc., would be always high of such designs, because these are all analog. So most of the times the transistors are on, and they're always trying to pull down the values from the active on resistors. So that's why the power consumption is quite high. Anyhow, so as of now, just remember this DAC, and we will make us use of this DAC later. Okay. Okay. Now I wanted to show you the IO pad design and a little bit on the IO pads. How many of you are familiar with IO pads? Are you guys familiar with the IO pads? You can come verbally, or you can type your messages. Swati, are you able to hear me? I'm sorry, I didn't saw your message.
Yes, sir, I can hear you, sir.
Okay, thank you very much. Okay, IO pads, you guys are familiar with the IO pads? No, I got few no's. Okay, no problem. Okay, I believe you are able to see my browser, and yeah, I believe such kind of EEPROM ICs. Okay, I believe such kind of EEPROM ICs, you must have seen it, right? This thing?
Yes, sir.
Okay, great. I think in your classrooms or in your labs, there must be some EEPROM ICs, which your teachers must have said that these are ultraviolet visible ICs, right? So those are EEPROM ICs. So they have EEPROM cells through which the ultraviolet rays can pass through, and they can erase the voltage present in the EEPROM gate. But at the same time, through that glass window, we can always observe that there are some thin wires coming from the pads and touching the IC. Okay, so what these are generally gold wires. Okay, so what they do, the chips always, if this is your chip, so you have metal terminals on the corners or edge of the chip. Okay, so inside that chip, what happens? These terminals come inside on the circular periphery of the die, the silicon die, which is inside the body of the IC. Okay, and a gold wire connects from this terminal to IO pad of the chip. Okay, so that is input output pad of the chip. Okay, and this is how something it looks like. Okay, you might get a lot of zoom views and from here. Okay, so this is the kind of soldering which is done from the chip to the IO pad level. Okay, so that if this is soldering done, so what is there in the corner of this chip? Okay, so on the silicon die, on the corner periphery, I mean like entire periphery, they are like square IO pads. Okay, maybe let me see if I can find any picture. Yeah. Can you see this picture on the right hand side of my browser? So you see these are IO pads. These are IO pads on which there is a thin metal wire which is being soldered. Okay. So not hand soldered, it is generally machine soldered. And these days, different techniques are used to solder the IO pads to the wires because the IO pads also shrinking day by day. They are making smaller and smaller. So the techniques are different. But the question is that how these IO pads are made and how do they operate and what they consist of and blah, 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 blah. I mean, like there are a lot, many number of questions attached to this IO pads. Any questions on understanding this IO pad? At least on the definition level. So these are square metal pads, okay, through which a silicon chip output or input is connected to the IC's body chip pin, okay. So using a thin gold wire or some anodized aluminum specialized wires, okay, and this is how it looked. This is how it looked. You know, this is an IO pin or input pin, anything it can be, and thin wires are shorted from here and connected to the output. Is this understood? First of all, let me see. Any questions? I'm sorry, I saw the message now. I was totally into explanation. Is my voice better now? Okay. Swati, Abhishek, did you get this? That I was talking about the IO pad? Okay, that these are metal pads through which the IO pins are connected, and using the gold wire or something else, the soldering is being done using machines, and you get to connect the chip IO with the IO of the package. Okay, this is how they look like. So now the question is that how do you make IO pad? So generally IO pads are made very big in size. At least, I mean, don't look into my physical display of the size, not definitely by my hands size, but they are quite big in number, quite big. I mean, and the designer has to specify the size of the pad based on the machine accuracy through which it can handle, because your machine is able to solder a particular, he can travel a minimum distance, yeah? Soldering each IO pad, you know, soldering, hot soldering like this. So how accurate your machine can move, okay, and how accurately it can solder the center point of each IO pad. Based on that, the dimension of the IO pad is being given. Okay, generally it is in microns and big in size as compared to your chip design. They're quite big in size, okay, so that the machines can solder it. Secondly, the IO pads generally are nothing but like a simple layer of metal, okay, through which you just connect and solder a wire, okay, and that can be any of your top metal layer. Generally, as the machine is going to come and impact it, okay, so what may happen due to impact, the metal can break or it can crack. So generally you don't put a single layer of metal, but you put all the metal layer beneath. So generally on the IO pad, you have metal 1, 2, 3, 4, 5, 6, 7, 8, or all the layers which are generally used in your fabrication process, all the layers, okay? So generally if you see a cross section of an IO pad, you should see all the layers of metal, okay? So enough of this. So let me explain IO pads step by step. So let me come back to micro vent. Are you guys able to hear me? Because I see a message from that my
Yes, yes, sir. We can hear you, sir.
great. Thank you very much. Okay.
Sir, I had a small doubt, sir.
Yes, please.
Sir, why is the EEPROM made like that, sir? Like there
Glass
should
window.
be, yes, sir. Like why are the wires attached to it instead of fabricating it within, sir? Like
Hmm. Okay. The question is that why there are wire inside or why there is a glass on top of it.
sir, I understood that the glass is used to erase the
Hmm.
content within it,
Hmm.
but why is it made like that, sir? Like that only the part which has to be lighted to erase it that can be outside, and the remaining can be embedded, no, sir. Why are there wires hanging out of it? Like why is it made like that, sir?
Okay. Actually, let me explain it back because something I'm missing. So generally, this is your entire EEPROM. Let me take it to it. Something better image. Okay. So if I put forward, can you see this EEPROM image?
Oh, okay, sir. I thought
Inside,
they only manufacture it that way, sir.
no. Inside the glass, below the glass window, this is the entire chip. There is nothing else. Okay. Below the glass window, this is the entire EEPROM memory chip. There's nothing extra inside this. There is nothing extra. Okay.
Okay, sir.
And secondly, you see these are IO pins which you use to insert on the PCB board, right?
Yes, sir.
Okay. As you can see, these are all in array. I mean, they are on a linear side of the wall, and these are quite wide. They're quite wide. I mean, 1, 2, 3, 4, 5, 6. There are 14 wires or 15, 16 wires on the side of the chip. Okay. Now, if I have to solder from one corner to the center of it, it becomes very difficult, right? So what they do is there is inside IC IO layouts. Yeah. Do you see this one?
Yes, sir.
So if you cut open an EEPROM, if you break it, so this is what you will see, that this terminal which is there, each pin which you insert on the board, okay, so this is physically goes to the center of the chip. Okay,
Okay.
it goes, just like a wired one, it goes to the center of the chip, and all the 16 wires or 28 wires or whatever the number of pins the PCB, I mean the IC has, all they come on the circular, or you can say, I mean, on all sides of the silicon layout. And from that silicon layout, you short using a gold wire, something like this. All of them, they come on inside line, and then you just short it. That's it. This is how it is.
Sir.
And there is no other way of doing it. This is the best method possible. Okay. And generally only in the EEPROM you put a glass window. In rest of the chips you don't see a glass window because they don't require it.
Yes, sir.
They don't need UV. They cover it completely. Okay. So let's go to the example. Okay, so I come back to micro layout here, And let me make an IO pad and try to understand how it goes further. Okay, so I'm using a 0.12 micrometer technology. I go to MOS generator. I think you guys are familiar with MOS generator very well now. You have used a MOS and capacitor from here. Now I go to pads. Okay, then I can just ask him to that generate a single pad with a size of maybe 20 micrometer, not more than that. Okay, and just generate and place on the clipboard. Okay, maybe this was quite big. I can make it a little smaller. I go back to pads and instead of 20, I make it 5. Yeah. So it just looks a simple a metal block, which you guys have already done a number of times. Okay. But the interesting fact will come up when we take a 2D cross section of this from the center. So what do you see here? Okay, you see here the stacking of all the metal layer, metal 1, 3, 4, 5, and 6, and all of them are connected through a wire, and this wire is also a big one. It's a very broad one, very broad one. Okay, so that he can easily connect all the metal layers, and when the machine will touch this IO pad for the soldering purpose, obviously there would be an impact, and that impact, I understand that will be very light and featherweight impact, but still for an physical chip which is so small and so small dia and so thin tracks, it may cause some damage. So having all the metal layer will reduce the impact, and hence the chances of breaking of the IO pad is very less. Okay, so I believe everyone is clear with this IO pad concept. Anyone would like to put up some question that, sir, mujhe nahi samajh mein aaya, like, or something like this? Okay, great. So your IO pad will look like this. Okay, if you want to say make a chip, okay, and want to have an IO pad, you can just go to MOS generator, go to pad section, and say I want a pad ring this time, and you can specify that how many pads you want in X direction. So you can say that I want only 2 pads in X and maybe 3 pads in Y direction. You can specify the width of the ring. You can just say it is 10 micrometer and only 1 pair of VDD VSS. That's it, and say generate. So do you see this one? Okay. So he makes the entire pad structure for you. So on the x-axis, you have 2 on the upper side, 2 on the bottom side, and on the y, as I said that I need 3 pair. So 3 on the left, 3 on the right. Okay. So that means, and plus 1 pair is of VDD VSS. Remember that. I asked him to make only 1 pair of VDD VSS. So on the right hand side, do you see the right hand side? These 2 pads, these are VDD VSS pads. Okay, so if I double click on one pair, sorry, micron becomes a little slower because of heavily loaded area and not my number of metal lines. I double click on one of the pad, to show me the. So you must see that on the right hand side, it shows that this is a VDD pad. Okay, are you guys able to hear me? Sorry, Kalpana, I saw your message right now. You asked me this question, what is V1, V2? Where did you saw that? Are you guys able to hear me? Because I got a message about my internet connectivity. In 2D preview, okay, we see it again. Okay, if you guys, okay, thank you, Abhishek, for the confirmation, because I just wanted to make sure that my voice is audible to everyone. Okay, so I enabled to ask him to show me that what is beneath this pad. So he shows me this is the VDD pad. And what do you see of the VDD pad? Do you see that this is highlighted? and you see that there is a blue ring highlighted across the IO ring. So what he does that he has made a pad of VDD and he has made a ring calling as a VDD, and he has connected that ring to the pad. So if any, and you will place your circuit in the center of this ring, okay? So anywhere you require a VDD, so you have to just connect a line, a metal line to this IO ring. That's it. And this would be the VDD line. So anywhere you need a power supply, you just go and connect it. So just like running a power supply across the circular path of the entire IO chip, and wherever you require VDD, just connect to it. That's it. Okay. Now, if I ask him to show me the bottom one, okay, so here's highlighted the bottom one pad, and here we can see that another ring highlights, and that is the outermost ring of the IO pad periphery. And this, you can see the properties are shown as ground, or you can see it's named as VSS pad. So this is the ground pad. So anywhere you require grounding anywhere, so you in the circuit, you can just travel to this mark and just connect it. And generally these are of the both layers. If I take a 2D again of this layer, so here you can see this is a metal 2 line, okay, metal 1 line, which comes to here, and rest this is the IO pad on the right hand side, okay. Maybe I can just show this. Yeah. So this is all metal ones, okay. Okay, so this is Abhishek, you asked me that what is V1, V2. So this is wire 1, wire 2, wire 3, 4, and 5. These are all wires, wire numbers. And metal 1, metal 2, metal 3, metal 4, metal 5, and metal 6. So these are the metal lines. So if I just zoom in this area and ask him to show me the 3D view, so you will take slightly little time to compute all the three-dimensional view of the design, and should show me any time now. Yeah. Okay. So there you can see that how it does. So these are all metal structure. Maybe I can just zoom out a little bit. Now I can ask him to show me the 3D view. Yeah. So here you can see that. Okay, zooming becomes an issue. Yeah. So here you can see these are the metal lines and on top of each other, and they stack together to make an layer of it. And here you can see the metal 2 is used to route through the layer, and these two layers are for VSS and VDD pad. Okay, maybe you can see at your ends to later words to realize how they work. Okay, so if we can see through this, okay. So this is metal 1 and this also metal 1. They're separated by both some ring, and anywhere you require ground and VD, so you can just come and short it to this. Okay. Okay, so this was the pad ring. So you have to perform an experiment where you just connect your inverter or maybe any of your design output NAND node or anything like that to an IO ring and see how does it works. The best suited would be you just make a NAND gate and make an IO ring and connect to it. Okay, so let's do this experiment. Okay, so I just do it first at my place. You guys can just follow through later. Okay, don't immediately follow me. Okay, first observe it. Maybe I just close micro and start again to see how it comes. Why is giving me this message again and again anyhow? Okay, so here we do is I have started my current, so by default it's starting 45 nanometer. It's okay, I think you can use the same one. There's no harm in that. But just keep your pen and paper ready, because there might be some things I may notify you guys to do the same. If the values are different, then what will happen? Your pattern will be so big that software simulations will take a lot amount of time. Okay. Okay. So let's do first. Make and pad ring. Okay, so I just go to, you have to just follow it. Okay, later word, not right now. You just observe it and make it later. So first of all, you can specify the pad over here. So you can just say 5 micron here, pad ring size. I don't think so it'll make any impact, but still, yeah. Yeah, so you can, as we are making a NAND gate, so NAND gate, we require 3 IO pins. Okay, only 3 IO pins we require. Okay, so I can just say pad in X is 1, pad in Y is 1. So you'll have 1 in X, right? Okay, 2, 3, 4. You will have 4 IOs, whereas you require only 3. Then ring size, you just make 2 micrometer and just give one pair of VDD VSs. So this is, you have to remember, that's it. I mean, like, you need not to follow as it is. And then you can specify the supply voltage is only 1.2, because your design works on 1 volt. So best suited is 1.2 as of now. Okay. So this is the size of my pad ring. So I just save this file somewhere on my desktop. There's my working folder. 6. Okay, so what I do is I have just saved it somewhere on my desktop. Okay, and here you can see that this is my VDD VSS pair. Okay, so if I double click on this, so it shows me that this is my VSS. Okay, and this is my probably VDD now. So what I do, I just zoom in this area of the pad so that I can just understand how this connection happens. So here it's mentioned that this is metal 8. So, okay, so this is metal 7, or maybe I can just take a cross section and see what is beneath this line. Okay, so this is metal 1, metal 2 is there. Okay, so this is using metal 2, and if I select this bottom line, okay, so again it shows me, or maybe I just take it 3D view opinion. Okay, I just take a 3D opinion. So he's using metal 2 and metal 1 to connect this, and the metal 7 and 8 ring is also there. Okay, so I can take any one of them. So this is taking metal 1. He's taking metal 1. Yeah. Okay, so if you click here also, you can see that. Okay. Okay, now what I have to do, first of all, I will just ensure that my NAND gate is working great. Okay, so I just go to file, open, and on the desktop where I have stored my gates, so there is day 3.1 NAND gates. That was my NAND gate. Okay, so what I do, I just clear these IOs of this NAND gate so that I will simulate as it is. Oh, first of all, I just verify that my delays were, what are my delays values. Okay, so I just open this and simulate this, and I see the delay values are coming around 3 picosecond. Okay, just remember that 3 picoseconds. Okay, now what I do is I just remove this inputs and outputs. I just clear it so that I get a smooth, clean NAND gate. And maybe I remove this VDD VSS. I just remove this VDD VSS. Okay, these are not required anymore now, and I just save this file. Then I open the design again of my IO, and I just go to file, insert layout, and I find that NAND gate design and open it. So let us see where he has put. So you can see on the right hand side corner side somewhere he has placed it. Ooh. So do you see this comparison? Do you see a dot on the right hand side bottom on my mouse? Do you see that one? Are you guys able to see? Anyone can confirm that? Are you able to see the right hand side bottom, a small dot?
Yes, sir.
Yeah, so that is my NAND gate. So you can compare that my NAND gate design is so small and my IO pad was, I mean, tremendously big. So that was enormously big, and definitely this was designed for making, thousands of NAND gates can fit into this pad ring. So maybe I can just clear this IO ring and try to generate back again to make something smaller. So pad in X is 1, in Y is 1, and the ring width can be, instead of 3, I make it 0.1. Okay, let me see how big it makes this time. So he's generating it one by one. Yeah. And now I insert the layout NAND. So comparatively, I think the ring has made smaller. Maybe I can make it more smaller so that things looks proportionate, not proportion, but at least something smaller. I didn't want it to have very big one. So pad in X, Y, and ring width instead of 0.0, 10 times smaller, maybe 0, 2 maybe. Okay. Okay, I'm back. Let me see. Prajwal. Hi, Prajwal. You there? Hello, Prajwal. Prajwal.
Yes, sir.
Hi. Can you make me host, please? Just go to participants window and you must see my name and just right click on my name and search for all money. Okay. Thank you. Okay, great. So let's start. Sorry for my internet connection. So it got weakened. And yeah. So we and trying to insert an AND inside a card ring. We can definitely reduce the size of the ring a little bit proportionate, but we cannot make that smaller that just slightly bigger than NAND gate. Oh no, that's not possible because you need to have pads which are significant big in size. So we were trying to reduce it. So I was just using, I just go to my data and go to pads and set one pad in X, in Y, and one, sorry, the ring is 0 time I try. So I just say again 0, 5, something 10 times more. So this small size probably.
So your voice is breaking.
Okay. My home Wi-Fi is lost, so connected through mobile network. I can just position of my phone. Okay, so let's see. I hope it's better now. Okay, so I made it something more small. And I see that yes, there is a small nudge, something I see, and I identify that's in NAND gates, which is very
So your
so
voice is bad.
okay. Looking at my video, is it better now? Anyone can confirm the voice?
Sir, screen is visible, but audio is getting clipped.
Okay, audio is getting clipped. Okay, let's take a break of 5 minutes. Maybe I just check my home internet, try to reset the router. Okay, let's take early break.